selected. Okay. Okay, finally I have the internet back. Do you guys have Wi-Fi? Okay, cool. Let's get started. Last week we talked about the stack cookies and how to bypass it. Looks like most of you get the homework right, and many of you actually develop an automated script to guess that, which is very good. So a little bit of announcement. So next week we are going to have the midterm CTF. It will be in class. So 2 hours and 50 minutes. There will be 4 challenges, 4 CTFs. And the rule is very simple. You are not allowed to talk with anyone except me, and I will have several PhD students here to proctor the exam. So you can talk to them, you can talk to me, you can ask some questions. If I feel I want to give you the hint, during the CTF, I probably will give you some hints there. You are not allowed to communicate with anyone else, okay? You cannot email the challenge to someone and ask someone to solve that for you. You cannot ask your neighbors to do this for you. Everything else you can do, okay? You can Google, you can refer to our previous lecture notes. You can also check your homework. That's fine. So it's the same as all kinds of CTFs. So basically, you are playing. Once you are playing as a team, you are the team. So you cannot collude with any other team. Besides that, you can do anything you want. So those 4 challenges, they will be modified versions from the homework, from the examples we demoed in class. So as long as you really understand what's going on with the homework, really going to understand the examples I showed you in class, it should be okay. And you have plenty of time, okay? So 4 challenges for 2 hours, 50 minutes. For some of you, so you really understand what's going on, you probably can finish everything in 30 minutes. But if you do not spend enough time there to understand what's really going on, you probably cannot solve them, no matter how much time I give you. So 2 hours, 50 minutes should be enough. Okay, so what we discuss this week will not be on the midterm CTF. So everything before will be there. So today we will talk about other defense to defeat buffer overflow, and we will also spend some time to develop your own shellcode. So the defense we talk about today, they are not only here for defeating buffer overflow. They are also used to defeat many other attacks. So the very first one is called address space layout randomization. This is also a defense that has been deployed on all our modern systems, modern operating systems, like the Mac you are using, the tablets you are using, even the phone you are using already have this. This is not used in low-end in IoT devices if they are using microcontrollers, because microcontrollers, they do not have a memory management unit. They do not have virtual memory. The memory address for those are very small anyway. There are some research try to randomize things there, but they have not been really deployed in real-world systems. However, for the laptop, phone you are using, it's already there. A little bit history about this solution, ASLR. So this was proposed 20 years ago. There was a team called PAX. They submitted a kernel patch to Linux, and that is the very first version of ASLR. And they coined the term ASLR there. So obviously, that's the very first version only works for applications. Only randomize the address space for the applications. They do not randomize the address space for the kernels. So most of the systems some of the systems we are using right now, kernel are also randomized, but user space, all of them are randomized. Then this solution find its way in OpenBSD 2 years after that. Then 2005, Linux kernel finally accepted it as 2.6, right? So right now we are at Linux 4.0 something. So it has been deployed a long time ago. Then Windows actually, Vista brought it into the kernel. So kernel was partially randomized as well. iOS 5 have that in 2011, also Android, and also back in 2014, Linux kernel 3.14 also support some kind of kernel address space layout randomization. Like I said, still they are not well supported in our embedded devices, those IoT devices. So IoT still is a buzzword, right? So many people talk about IoT devices, but there are many different levels of IoT devices. There are IoT devices that are very low end. They are still 8-bit CPUs. Those CPUs, there is no virtualization. Then there are 16-bit CPUs and 32-bit CPUs. Even for 32-bit CPUs, most of them do not have memory virtualization. So one of the very popular IoT CPU is called ARM Cortex-M. So all your phones, most of your phones, maybe 99% of your phones are using Cortex-A CPUs from ARM. Of course, the manufacturer could be Qualcomm, could be other companies, but the CPU is an ARM CPU. That's a Cortex-A CPU. That's a very powerful CPU, 32-bit or 64-bit. But there is another Cortex-M CPU. There are maybe 10 different models of Cortex-M CPU. Those CPUs, they are called microcontrollers, not microprocessors. They are all 32-bit, no memory management, but there are hundreds of billions devices using Cortex-M CPUs out there. Most people do not know. So even on your phone, there is a Cortex-A CPU. There could be several other Cortex-M CPUs as well. In our infotainment systems, in our Amazon Dash, and some VR devices. There are a lot of those Cortex-M devices. So the security of those devices was not a problem before, 10 years ago, because they are deeply embedded. They do not face internet directly. But now those devices, they are connected to Wi-Fi, they face internet directly, so they are exposed to all kinds of attacks. Those devices still, they do not have this defense, the defense we are talking about today. So, so to understand how this defense works, let's just think about how the attacker can really take control of your computer. So previously, what we did, we can say two main approaches. One is code injection attack. Another is code reuse attack. In code injection attack, you inject the share code to the address space, and you put a huge NOP SNAT in front, so to increase your chance to jump to the share code. So that can be defeated by using things like data execution prevention, DEP, right? Then people find another approach is to return to libc. We can return to the code that is already in the address space, like the system call or other, the system function call, not the system call. The system function call and other things. But as an attacker, to pull off that, you need to know where is the C library function system, right? You need to know exactly the address of that function. And for this one, there is no chance you can put a NOP SLAT in front of that. So share-code 1, you put a NOP SLAT to increase your chance. You don't have to know exactly where your share-code is. But if you want to jump into the C library function system, you have to know exactly where it is. You cannot change the code. You cannot append some NOP SLAT there, right? So you have to know the address. So for most of systems, those addresses are, for old systems, those addresses are fixed. They are always the same. So if an attacker analyzes his own system, then he knows how to attack your system, okay? So the defense here is very straightforward. We just randomize those addresses, make it much difficult for the attackers to guess where that function is. This is not perfect. Still the attacker may guess correctly, but the chance is very low. Think about the huge address space. If you can fully randomize this, the chance for the attacker to guess that is really low. However, I will show you in today's class that in the systems we are using today, the entropy for those randomness is still small. We can still guess it. Okay. Another related concept to this is position-independent code or position-independent executables. So they are basically a sequence of instructions that they can execute properly no matter its address. Okay, most of the instructions you have seen so far, they are already position-independent. For example, if you add two registers together and EAX, EBX, that instruction can execute properly, correctly, no matter where it is, right? It has nothing to do with where it is. But some of the instructions are different. For example, a call instruction may call into a relative address. The offset to its its current location is encoded in that call instruction. Some other instructions, they will use like a PC or EIP to find other resources in the memory. So those instructions, obviously, where they are at is predetermined. It's compiler needs to carefully determine where those instructions are at. Or the compiler will need to calculate the offset for the resources it's going to access. So those instructions are not really position independent. So position independent code, position independent executable means when we compile a program, the output, every instruction in that program should be position independent. For example, this is a old This is a figure I showed in the very first class of this semester. This is the address space of a 32-bit Linux machine, something like that. Windows is also similar, actually. So this is 32-bit, so the memory space is only 4 GB, and they kind of follow this kind of layout. And the very low memory areas, we have the application, the L file, noded from the L file. Sometimes we call them program modules, because those are the parts developed by the programmers. Those are not the libraries. Then there will be data sections, BSS sections, then there will be heap, then there will be memory mapped segments. The memory mapped segments are usually for C libraries or other shared libraries. You use the mmap system call to map that. So you map a file into the memory address. Then after that, we have the stack. The stack goes from higher address to lower address. Then the most higher 1 GB is reserved for the kernel. So that is the memory address space we used for many, many years until we started to deploy ASLR. So in that address space, what we usually do is we will load your program to a fixed location and load the data BS to all of those to a fixed location. So every time that program runs, it will have the same address. So far, all the programs you have been hacking is like that. Every time you run a program, it is loaded at the fixed address. But later, also I want to talk about the static programs with shared libraries. So static programs with shared library means you do not use dynamic C library or other shared library. The C library will be part of your program when you compile it. So your program will be huge. So you only write several lines of code, but you link the whole C library there. So your program will be huge. So when the program runs, the whole thing is loaded into the memory space, and those libraries are not really shared among different processes. So for those programs, the libraries are also loaded to fixed addresses determined by the compiler and also the linker. Then we have the new program that cooperate with the OS to randomize its address. So this needs the cooperation between the operating system, the kernel, at runtime, and the compiler. The compiler needs to make sure the program is position independent. So you can compile your code as a static program. It's not position independent. But the C library could be position independent. In those cases, your program will still be loaded to fixed location, but the C library could be loaded into different addresses every time you run it. So to fully take advantage of this security feature, so even if the kernel supports this, if your program is not compiled that way, you are not fully utilize this feature. So to fully utilize that, you need to compile your program as PIE, position-independent executables. Then when your program is loaded, the kernel, every time when the program is loaded, the kernel will find a random address to load your program, load the libraries, okay? That sounds perfect, but you will see that in existing implementations, we are using Linux, in Linux implementations, you can see the entropy is not that high. It's not going to put it at a random address at the full address space. Okay. So this is the first piece of program we're going to look at. This program, very simple, don't do anything useful, just show us the addresses of different functions and the variables. Let's say we have two global variables. One is k. That one is initialized. So that one is supposed to go to that .data section. The other one is not initialized, called L. That one is supposed to go to the BSS section because it's not initialized. Then there is a pointer, global variable pointer P. The pointer points to a string. The pointer goes to .data section. The string itself also goes to the .data section. The pointer has the address of that string. Then we have three functions. One is add, another one is a sub, then we have a compute. You can see those functions are just printing out the address of a local variable here. So here we have a local variable I in AND, we print out its address. Then we have a local variable J, we print out its address. Then compute, we just call those two. So that's it, okay? So in the main function, we try to print out the address of everything. We first print out the C library functions here. So right now, we're going to compile this program using three different flags. We're going to compile it as a static one. We're going to compile it as a static one without position-independent code, and also a dynamic without PIE, and also with PIE. So we are going. So first is we have the C library's address. We have the printf set. That's my Dropbox. It's asked me to input password. Anyway, so we print out the address with printf, memory copy. Then we calculate the difference between them. Then we print out the address for system. Then compute the difference. Then we print out those module functions. By module, I mean in the developer developed ones. Then the main function, add function, we calculate the distance. We also calculate the distance between several other functions. I forgot to calculate the distance between the library function and the module function. Oh, I should do that, but okay, whatever. Then global function, global variables, uninitialized global variables, then local variables, right? So that is just the program. So if we go to our server, it's in. I'm a little bit slow today. I'm a little bit sick, sorry. So a little bit slow. We're looking at this one, okay. So let's look at the 32-bit. Maybe we should look at this one. ASLR 1, no PIE static. So this one is compiled statically. So if we do a file on this one, you can say this one is statistically linked. So the C library is part of this file. So if we do a ls, we can say, you can see the file size. Should we do H for human readable? Yes. You can see the file size. The source code I show you there is very small, right? Just one or two files. But the file size is 70K. The reason of this is because we link because this is statically linked, the whole C library is linked into this binary. That's why it's big, 1700K. So if we run this program, you can say the address of printf is this location. The between is this address. So nothing, it's quite normal. But if we do a nm on this one, so nm will show the symbols of this program. So if we do nm here, we will be able to say the address of all those symbols. You see, those addresses are not offset. They are real address. But when I do an nm, I'm not running the program, right? I'm just analyzing the program, which means the address of those functions are determined at a compile time or link time. When you load those programs, when you load this program, this one probably is, some of them are functions, some of them are just variables. they will just have this fixed address. No matter how many times you load it, they will have this fixed address. But if we go to a dynamic linked version, especially without PIE, with PIE, maybe this one. Oops, go here. So now we run this program, let's see. So let's see, where is it? I run it twice, right? Okay, I run it twice. So you can see that the first time I run it, printf address is F7D6C340. And the second time I run it, the address has changed. It's DE1340, okay? It's the middle 3 characters. So at least 12 bits are changed. So the entropy here could be 12 bits. It's not very high. 12 bits is like what? 4K, right? 4K. So it's not very high. But still, you can say they are randomized. By the way, the TA just enabled the ASLR before this class. He enabled it at 5 o'clock. That's why those addresses are changed. So previously, if we were run the same ones, they will have the fixed address because we didn't enable ASLR at the kernel. So you can see that they are changed, but let's say the offset is not changed. The printf and the memory copy, their offset is this. The first time we run it, the offset is this. It's F because F is basically a lective number, right? So one is higher than another. And the second time we run it, it's the same number. Is it too small, or you guys can see it? Okay. So when we so you can see the current Linux system, we randomize that. It's not randomized at the function level. It's just to randomize the whole C library. Put the whole C library at different address. So the granularity is not very good. Obviously, we can randomize at the function level to make things even more randomized. Or others, you can say, let's say the module, the main function. Here we have 5660 B8AD. And the second time we run it, it's a different address, 5658 D2AD. Those are different. Okay, ASLR is working, but it's not like it's super secure. So if we do an NM of this one, you can say the results are different. You do not see those. First of all, you do not see many symbols anymore. So previously, when we do that, we see many symbols. And they all have fixed address, 08 something. That's a fixed address. Now when we do this, they do not have a fixed address. They only have an offset. So it's a very low address because that's an offset. That's not really the address when you run this program. So it's the same for 64-bit. Let's say this is a 64-bit. It will be the same. We run this program twice. Did I run it twice? What's going on? One more time. Okay, here. So for 64-bit, you can see the address obviously is much longer, but so the address of compute, here we have this number, here we have a different number. You can say, starting from the second byte here, previously we have 60, now we have CD, EA, for several characters, they are different. The randomness, the entropy is a little bit higher here, right? So that is basically how ASLR works at at the system level. And I'll show you one more example about so previously we have seen this function called get PC sunk AX. So I told you the reason to have this function is just to, at runtime, get the address of itself. And you see here, this function try to get the relative address, or maybe the address of this own instruction, and put that in AX, then add this fixed number to EAX. So the purpose of this is some resource instruction is going to access, maybe a string, a local variable. That resource is still placed at a fixed offset to that instruction. But at runtime, to access that resource, we need the absolute, the full address. But we don't know the address at the compiler time. So when we compile it, the compiler will instrument instruction like this to get this instruction's address, then add some offset. That offset is fixed to that address to get where that resource is. So when you say function like this, don't be surprised. There are many functions like this for different registers. For example, this one is getting into EAX. Then there are others as well. Let me show you the core instruction. So you have been saying this instruction a lot, but we never really look at the encoding of this instruction. We understand how this instruction works at a high level, but if you look at the encoding of the instruction, you can see that this instruction can have different opcodes. So with eight opcodes, they are all core instructions, but they are slightly different. For example, the first one, E8, E8CW or E8CD. CW? Okay, what is W? So W here is not really the W is, I'm not sure what is W here. Because, I mean, it's hex. It cannot be W, right? So it's maybe just the number. So anyway, so this one, yeah, maybe just the number. It shows the number should be a wide. Oh, I think so. Yeah, I think it's an immediate number, but the number should be wide. It means 2 bytes. Then this one probably D means should be double word. This one should be word. W should be a word. D could be D word, double word. So it's 32-bit. So anyway, so the opcode is E8, and after E8 we have 2 bytes. Then that 2 bytes is not the absolute address in the address space. It's a relative address. Relative address to the instruction's current address. So you can say this instruction, it is a position-dependent instruction. Some of them are not. For example, this one directly calls a register. Then you can put the full address into the register, not the offset into register. So this one is not position dependent, but some of them are. So when compiler generate codes, it will avoid generate PIE code. It will avoid generating using those opcodes, but other opcodes. So the overhead of PIE, someone measured it. It's not really high. For 64-bit, the overhead is only 1%. I mean, runtime overhead, of course, at a load time, when you load the program, the OS need to randomize the things, or the loader, not necessarily the OS, need to randomize the things. That will take a little bit more time, but that's just once. You don't do that very often. Of course, another approach is to make this even more secure. Even the program is running, you probably want to think, can I randomize it after 2 minutes of running. Can I randomize that? That's also possible. Okay, but those are more advanced topics have been discussed in literature. Some research papers doing something like that. So for 32-bit, the overhead is also just 3%, so still acceptable. So for your own computer, if you are using Linux, if you need a root privilege to disable and enable ASLR, then you just use those commands to disable and enable that. By default, those are enabled. For this week, we are going to enable that in our system. And for the exam, midterm, CTF, we are going to disable that because this is not part of the midterm CTF. Okay, so we just saw how it works. Like all other indirect defenses, it still can be bypassed. It can be defeated. There are many ways to do that. First is the program may have some vulnerability to allow you to obtain the address of everything. So if you know the address of the target system function, if you can, then you don't need to guess, right? There is a vulnerability to disclose that, then it's okay. Then, and some vulnerability, sometimes you only need to know a relative address, don't need to know the absolute address. Also, the implementation, the approach sounds good. It's not a direct approach, it's not perfect, but it sounds good. There's some randomness there. But the implementation may be weak. Even if it adds randomness, the implementation is so weak that you can easily bypass that. And that's what we are going to do in the ASLR level 2. And the Linux system we are using our server is state of art. It's at least just 1 year old, I believe. So it's still state of art. But you can say a state of art Linux system, ASLR, we can easily bypass that. So this is a vulnerable program. We have a main function requiring 2 arguments. Actually, 1 command line argument. Then it calls valfoo with your input. The valfoo will print out where the function valfoo is. Then there is a buffer. After that, there is a vulnerable memory copy. Then your goal here is just to print the flag. So you can return to print flag directly, or you can return to print secret. So if we run this on our server, level 2, so see, we have been running this for several times. Every time we run this program, valfoo has a different address, right? The first and second time was pretty close, actually, but the third time was much different. So you can see the random parts are here. So the whole address is 32 bits, 4 bytes. The random part is only in the middle, you see? 3 characters, 3 letters. So at most 12 bits. I believe it's not 12 bits because you can see this one is always 6 or 5. 6 or 5 there. So it's probably, here is only 1 bit different. So those 2 are every time as much different. So those 2 probably are full 4 bits, each character, each letter. Then this one probably just 1 bit, right? Sometimes it's 6, sometimes 5. So in total, it's just 9 bits of randomness. 9 bits is 512, right? 512. 9 bits, 512. So, which means if you guess a random value, it's 1 out of 512. So the chance is still very high. But for this one, how do we want to approach this? Let's say, let's look at the disassembly of this program. Looking at a vol foo here. We can say vol foo, it's this one, this address right now. Like I said, it's not the runtime address anymore, it's just offset. So vol foo will be called by the main function. The main function has an address 13B8 something. So after vol foo, when we call vol foo here. After vol foo, we're going to return to here. So it will be 1404. Then, so you can imagine what the stack of the vol foo looks like. The vol foo, on its vol foo stack, it will have a return address. And the return address will be this one, right? Whatever the address is at the runtime, so 1404 something will be higher. But this one will be added to a base number, so this may be, so 04 is for sure, but not necessarily 14 there. Then our print secret will be 13 something here, where our print flag will be 12 AD. So look at this source code. How do we print out the flag? The idea here is very simple. The relative address for those functions, they do not change. So the higher 3 bytes of the absolute address, that will be generated at runtime. But doesn't matter. We don't care about that. We only care about the last byte, right? So on vol foo's stack, what we will have will be some address. So we can debug this program. Let's debug it. We debug this program. We set a breakpoint at vol foo. Then we run this program with some just hello, whatever. So now we are in the function vol foo. To figure out its return address, we just need to exam whatever the ESP points to, right? Because we're at the beginning of the function, ESP points to the return address. So you can say the return address we have is B404. Then that must be in the main function. So if we disassemble main function, we can say B404. That's the instruction after we call vol foo. Of course, this address will be different every time we run it. So we want to go to print secret. Print secret address is B3 8D. The first part, the higher bits is not changed. So the idea here is we do not overwrite the whole 4 bytes of the return address on the stack. We only override the least significant bytes. And the higher bytes, we do not change it. We do not touch them. Does that make sense? But this one may not work here because here we have a B3. Yeah, I think after we update the server, let me run this again. Because this time we have B3. Because of the B3, they are not in the consecutive, they are not in 256 bytes there. We cannot override the B3 because we don't know that's B3. We only know that 3 here, but that 3 is only a half byte. We cannot override half byte. There's no interface for us to override half byte. So we run this again. Let's try again. So you can say this time Volfu is in 6411, but if we print the address, it will be 6404, but print secret will be 6380. So we will not be able to do this actually. Okay, so I need to update this program. The reason, so this challenge, I carefully designed that. So print secret will have the 3rd byte with the return address of Volfu. So you only need to override 1 byte. But because we updated the Linux, now they are a little bit off there. But because of that off, we cannot override this. Does that make sense? Because we need to calculate that, then if we calculate that, then, but we cannot put that. Okay, I need to change, anyway, I need to update this challenge. So you can try this. The exploit will look, the exploit will be very simple. The exploit will look like, so let's do obj dump here, Intel. So this is Volfu. Here is a memory copy. And you can say the buffer we're writing to is EBP minus 16. So you are still overwriting the return address. You are still just write some garbage to the saved EBP. But you are not overwriting the full 4 bytes of return address, only the last byte. So you will have 20 bytes of garbage, then just 1 byte, which is the last byte address of print secret. That byte doesn't change. Then you leave the higher 3 bytes of the return address on stack intact. Does the idea make sense? Yeah, but I need to update the program a little bit to make it work. So, like I said that, you can see the current Linux system, they only randomize things when you execute a new program. So it has the same problem as the stack cookies. The stack cookies we saw last week, the program will not get new cookies when the program fork itself to create a child process. And because of that, you are able to attack that. So for Linux systems, the fork also do not re-randomize the program. It will only randomize things when the program is first loaded. So this paper, published in one of the top conferences, NDSS, back in 2016, they propose to not only re-randomize a process for fork, they also re-randomize a process when the process is running. maybe for 5 minutes, the program has been running, then we re-randomize everything in the program without a source code analysis. So this is actually very difficult because you have to figure out all the pointers in the whole address space. Some of the code pointers, some are data pointers. We re-randomize everything. All the pointers still should point to the right place. And without source code, this is actually very difficult. That's why they published in one of the top conferences. Okay, are we good? Any questions so far? Okay, so after I update that one, I will pin you guys so you can try that in your homework. The next defense we're talking about is called Secure Computing Mode, or Seccomp. So this is also a Linux kernel extension. The idea of this defense is very simple. So process running on top of on operating system, and the process uses system calls to ask for services from the operating system, right? But in security, we have a principle called least privilege, which means if a process doesn't need some kind of rights, we should not give it in the first place. So if we apply this idea to process, the process, let's say you develop a simple process. That process will make system calls like open files, read files, that's it. When you develop that process, you never ask the process to fork itself. You never ask the process to create a new process to read the password, right? Then the process, but as an attacker, you can inject those share code there. The share code may have those system calls. But as a developer, you can relinquish those rights. You tell the OS, at the very beginning when the process is running, you tell the OS, my process will never make those system calls. If later this process makes those system calls, probably it's because it's being hijacked, it's being attacked, right? So this idea is like the firewall in network security. So Seccomp is basically building a system call firewall for all the process. Then it will allow developers to write rules at the beginning of the program to allow certain system calls, to disallow system calls, or even some very complex rules, like to allow or disallow system calls based on the arguments. So more fine-grained confinement there. So, and this solution is actually inherited by children. If you fork process, the child process will still follow this. So this was also proposed like 17 years ago. Was for public grid computing, like it's kind of before the cloud computing for those high-performance computers. We call it grid computing. And they have the needs to confine different untrusted programs. Then those idea was quickly merged into Linux kernel in 2005. Also, Android has been adopting this 5 years ago. So let me show you how this works. We are only looking at this at developer's point of view. We're not looking at this at a kernel developer view, how to develop this. Okay, from developer's point of view, this program shows you how to use it. So here we have we're going to compile this program into a disallow and a allow version. The allow version will not have the code in my sandbox. Okay, so we do not look at them first. So this program, the allow version will only have this. is going to execute a new program, which is cat. And we are going to cat the flag. That's it. So this program will run first. As soon as it executes, it's going to replace it with cat, with the argument flag. So it's going to cat flag. So it will print us the flag. So it will be this one, allow. So if you run this program, it will just print out the flag for you, the same source code. If we do a strace of this program, you can see that it's just a regular system calls. It will open file. Well, when we do strace, we don't have the permission. That's why it's permission denied. But when we run the program, it's a setuid program. It has a permission. So when we do strace, we don't have the permission. So the disallow version of this program, we utilize that Seccomp, and we add this piece of those 4 instructions there. So 4 statements there. So first we create a Seccomp filter context. That's it. Then we say the default rule is we are going to allow all the system calls. So we are going to action allow. Then we are going to add a rule here. The rule is we are going to, if there is a system call EXE we are going to kill this program. That's it. So we forbid this program to make the system call EXE. So this is a system call firewall. Then we enable this policy by loading this context. So when we compile this program, we get the disallow binary. The disallow binary is here. So when we run this disallow binary, and you can say the kernel Seccomp extension will kill the process and tell us that's a banned system call. It will actually give us a core dump here. Yeah, I guess they cannot give us core dump because they don't have permission to write this folder. Yeah. So that's how it works. If we look at the source code of this, let me show you the source code and you can see that this is the same source code. We just compile the same source code. You see the makefile, you can see the only difference is in the allow version, we do not define any macro. In the disallow version, we define the macro mySandbox. And because of that definition, this piece of code will be compiled into the program. So if we look at the system, the strace of the disallow version, you can say it's making the Seccomp system calls. So Seccomp itself is also a system call, right? Because it's a kernel module. The process will tell the kernel, this is a policy we're going to use, and it makes several system calls to set up that. So now we do not say, now we do, so for previous one, when we do strace, when we do strace, we were not able to read the file because we don't have the permission. Here, permission to read the file. So here, when we do strace, when we execute the system called EXE7E, the program is killed. We never have a chance to really try to read that flag file. The process can't was never created here. Okay. The previous one, the process can't was created, but can't didn't have the permission to read the file. That's a difference. Okay, so those are for differences. Like I said, those two differences obviously can also stop us to inject a shellcode there to stop buffer overflow to some degree, not perfect. Then let's take a 10 minutes break. When we come back, we will develop our own shellcode. Yeah, I just changed the ASLR 2. It should work now. I just comment out one statement there. Now we have, you see here, after valve is 13 FB, and the print is also 13. So they have, yeah, that should work now. Yeah, let me ask the TA to upload that. Okay, everyone's back. So I have asked the TA to update ASLR 2. He will update it later today. After that, I will send the exploit to you on Slack and via email, so you can try that. Okay, so the second half of today's class, we talk about share-code. So far, you have not been developing your own share-code. You are using the share-code I gave you. So in today's homework, we are going to develop a little bit share-code. There was a book, the Share-Coder's Handbook. It talks about share-code for different operating systems and different things you can do with share-code. But this book is quite obsolete. This was probably published 15 years ago. Also, there are websites collecting different share-code. It's called exploit.db, I believe. Exploit database. There you can find different share-code for different purposes, for different platforms. But sometimes they do not work, right? So you still need to debug the share-code to understand why it works or why it doesn't work. So this is the share-code you have been using many times. So this is a 32-bit print flag share-code. It makes 3 system calls. The last system call, the last one, is not really necessary if your share-code works. This last one is to exit the process gracefully if your share-code fails. It actually makes 2 system calls. One is open, then just a send file, just 2 system calls. The 64-bit version was similar. And you notice that the 32-bit version, there is no zeros, right? So this is the address. The address here doesn't matter. So when I compare this, I copy that, it has address, I copy the address. So the share-code itself is position independent. Doesn't matter, the address. So just ignore this column. But the second column is every byte of the share-code. You notice that here, this share-code, there's no zeros. There's no single zero. Why 0 matters? Because some of the vulnerability is a string copy. String copy stops at 0. So if your share-code has a 0, then you are not going to copy a full of your share-code. Let's say you have a 0 at here, the 10th byte. Then the string copy will only copy the first 9 bytes, not everything after that, right? So the share-code will not work. And our 64-bit version, the version I gave you here also, there is no 0 actually. Yeah, this version there is no 0. So, there could be many different constraints for share-code depending on you inject a share-code to the program. The program will treat that as a string. So the program may have some expectations for that string, right? So one of the strictest form of the constraint is the share-code, whatever you inject there should read like English. And someone back in 2009 published a paper on this. The paper title is just English share-code. So they developed a system to automatically generate share-code to do malicious things like get a share, to read a file. But the share-code, the ASCII of that share-code, read like plain text English. So if you are chatting someone on Skype or what do you use now? WhatsApp, whatever. They are maybe sending you share code. They are attacking you there. Okay? So this was published 13 years ago. So this is an example in their paper. So the whole thing here is the share code. It is readable. It's not good English. It may not make perfect sense, but it's still readable English, right? There is a major center of economic activity, such as Star Trek, which doesn't really make sense, but it's still readable, right? So this whole piece of saying is readable English, but actually it's, at the same time, it's share-code. So this is a ASCII of that. You can see that the blank part is actually the code, the binary code that can be executed. The other parts are just English. So basically, the last here would be just a jump. The jump will be jump to here. So in the middle will be just some fillings, some paddings there, right? So the blank part are the code that runs. You can say there is a major. If we translate that into opcode or to a assembly, that's actually a push. ESP push some value there, then do some calculation, and push then another jump. Okay. So this piece of code itself doesn't do anything crazy. It doesn't really make a system call here, you can see, right? So this example, specific example here, doesn't show its maliciousness, but they prove that this give us any share code. Their tool can translate your share code to readable English. So today, your work is to change the share code I gave you before. So for this piece of share code, there's no zeros, but it has many unprintable ASCII characters. Is that not printable? So we are going. Your job is to change those instructions and change them into all printable ASCIIs, which means, for example, there is push 67. If there is then you can say what is the character that. Maybe one character is not readable. Then you need to change that instruction to an equivalent instruction, but that equivalent instruction will not generate a non-printable ASCII. For example, C0, I believe, is not a printable ASCII. So you cannot use XOR EAX anymore. You have to, so the goal of this is to set EAX as 0. You need to achieve the same goal, but without using this instruction. So you can get rid of C0. So B0 probably is something also you need to get rid of, okay? So that's your goal. So how do you do this? This is basically the template, very simple. You just need to have a .s assembly file, then put your instructions there. You can, at the beginning, you can just copy those instructions there, those instructions. You can delete the last 4 instructions, last 4, because the exit, that's the exit. You don't have to use that one. Then you save that into a .s file. Then you just compile it like using those commands. For 32-bit version, you compile it using GCC. You tell this is a 32-bit version code, that you don't need standard library to link with this one, and you just want this program to be static. Then you have the share code. Then you have your source code in assembly. Then the output will be an L file. The L file's name is share code. You can change this. This doesn't matter. So this is an L file. Then you are going to dump the .txt section, which is a code section of that L file, into a file called share code raw. This is also a name you can change. And dump from this L file. So this one is an L file. This is just a binary, okay? This one doesn't have any header. It only has those instructions in binary, okay? Not the instructions in assembly, in binary. The 64-bit version is the same, okay? So how are you going to test this? We have several testers installed on our server. This is the very first version. Let me explain you how the tester works. So the tester is only one function in the tester. So the tester will just first allocate 1 page of memory, which is 4 KB. So that is big enough for your share code. Your share code usually just 20 bytes, 30 bytes. We allocate 4 kilobytes for you, so that's enough. In that memory location, you can read, you can write, and you can also execute. Then after that, usually it should be successful. If after it's successful, we allocated that page for you, we're going to read from std in, and we're going to read one page. Then we just give control to that one page. So no matter what code you gave there, we're going to execute it. So that's it. So you just need to pipe the byte of your share code into that tester. That's how it works. So that's you can say this is the first version of tester. Whatever gave to the tester, it runs. So if the share code has a 0, it runs. If the share code has printable ASCII characters, it also runs. So we have our second version, tester non-zeros. So this one, we're not using read. We are doing a string copy there. So, well, we first do a read. We read to a global buffer. Then we do a string copy to our memory page, which means if your share code has a 0, it's not going to copy the whole share code there. So it will not be successful. The third version is tester ASCII. So this one, similar. We read whatever you give us, then we will do an ASCII copy, which means we're only copying those printable characters there. Okay? So your job today is to pass this one, tester ASCII. That's part of your homework. And you are going to change this piece of share code. This is a share code you are going to, well, to make it easier, delete the last 4, right? You don't need those. The others, just change it ASCII. So here we have a CD. What is CD? I think I allow CD there to make it easier for you. CD x2 decimal. CD is 205. I think maybe the source code here is outdated. I think I allow CD there. Let me check. Tester long ASCII. Oh, yes. So the code we deploy on the server, you do not have to change those 2 instructions. So CD and 80 are allowed. So you do not have to change the int 80. That's a system call. Okay. But even we disallow you to do that, this is still possible. Okay. But it's much more complicated. So it's still possible. You need to, basically, your share code needs to change itself. You need to deal with a self-modifying share code to have a, because eventually you are going to make a system call, right? So eventually you will need that int 80 there. So what happens is your share code will first bypass this. Then after your share code executes, your share code will change itself to create int 80 instruction in the memory. So it's still possible, but I don't want to make it too difficult for you today. So you just change other instructions. Okay, let's start working on this. So you need to go to the server tester ASCII 34. That's the one you are going to use. Yeah, you can see here, we compare with CD and 80. So CD and 80 are a lot. That's a correct version of battery. Do you understand where to start? No word. I think you have to use this line after this line. Intel syntax, low prefix after. So in a template, after global start, please add a line like this. Intel syntax, no prefix. Otherwise, the default syntax will be AT&T. Yeah. So because this semester I switched to Intel. Using AT&T syntax. Just tell the compiler you are using Intel syntax to run the assembly. That's a problem. So if you are still a little bit confused what's going on, I suggest you to use our 32-bit share code and get a flag for tester run 0 first. So you know how to compile this, how to feed that to the tester, then you think about how to change this to the tester outside. give you a little bit of hint here. For example, the 32-bit version shellcode. So every byte should be between 0 to 7F, right? So you look at the first instruction, it's just 68767, so it's legal. Don't need to worry about this. The second instruction, you don't need to worry about this. The third instruction, the goal is to make year X 0. But if you look at both the two instructions, the goal actually here is to make year X 5, right? Put 5 into year X. We're using two instructions here. And those two instructions, there's a C0, there's a B0, we cannot use. So just to think how we can put 5 into year X and without using, without have those weird, those bigger bytes. So you can just try many ideas. For example, I will try push 5, then pop year X, right? So this will also put 5 into year X, but I don't know if it will have a non-ASCII, right? So I compile this, then I got the output will be 680558. It works, right? So you can try, so those two instructions can be replaced with these two instructions. You can also try, for example, you can push 55, then pop year X, and subtract 50 to year X, something like that. What should be the syntax here? What? So the problem is subtract. What? The dollar sign? Oh yeah, I need a dollar sign, but this one doesn't work because you see, it will generate a lot of zeros. We do not allow zeros. So maybe instead of using AL, it may work. Let's see. Still do not work. But this one is using DS, so that's not the correct syntax here. Oh, hold on. This is Intel syntax, right? Oh, sorry. This is Intel syntax. Should be like this. Huh? Still. This one should not be 40, right? Should just be. Oh yeah. For this one. This also works, right? So if I do push 55, pop year X, then I subtract 40 from AL. You can see the bytes generating is 683758 to say to 8. That also works, right? So your goal is to get rid of those bytes. So let's say after that, there is a 89 you need to get rid of. So this instruction you need to change. Also, this instruction you need to change. This one you don't have to change. We'll allow that. Then several, yeah. Just change. Well, a lot of instructions you have to change. Everyone after that. Well, there's another one is here. There's this BB. What is BB? This is 80. So this BB is actually this 1,000. I didn't really say 1,000 there because, so I just use BB. So this one doesn't have to be BB. It can be much smaller. And this one's go. See, this one is also moving something into AL. So as long as it's moving a constant into there, you can just do a push pop. We just showed you, right? So like here, you are moving 5 to AL, or you are moving a number to any register. You can just do a push pop to get rid of that. So, for example, this one you are making ECX 0, so maybe we can do a push 55, then pop ECX, then just extract CL40, 50 should be, 55, because we're getting 0. Oh, this one is big. those two works. So this one doesn't work. Maybe push pop, then we decrease ECX. May this one work? Yep, see, this one works. So I want to set something of 0. I push 1 there, then pop it to ECX, then I decrease ECX. I'm still setting ECX as 0, but I'm not using, so it's just 6A, those things, right? So this is where you need to test different instructions. Do you understand what problem?